Hello, and welcome to Differential Equations. This is Lecture 2, Separable Equations. All right, so last time, we talked about the classification of differential equations. Right, specifically, we talked about ordinary differential equations, or ODEs, versus partial differential equations, or PDEs. Remember, ODEs, where you differentiate only with respect to one variable, and PDEs, where you differentiate with respect to more than one variable. Then we talked about linear versus nonlinear, right? This refers to how the dependent variable, so say y, enters into the equation. So linear equations, you can have, say, cosine t times y. That's still linear for y, but you can't have things like y squared. And we talked about homogeneous versus non-homogeneous. Right, so when you have a linear equation, homogeneous is when your right-hand side, which is the term that doesn't have y or any of its derivatives, is equal to 0, and non-homogeneous when it's not. This time, we're going to be solving the simplest ordinary differential equations. Okay, so the simplest of all of the non-trivial differential equations is when you have an equation that looks like dy dt is equal to f of t. Right? Which we solve by integrating both sides with respect to t. So recall here the two notations we use for this. Right? So on the one hand, there's the antiderivative notation. Where we might write y is equal to the integral f of t dt, right? And here, the right-hand side is merely a symbol that just stands for any function whose derivative is f of t. The other notation is the definite integral. Right, where we would write something like y of t is equal to the integral from some initial point, say t naught, to t, f s ds, or some other dummy variable, plus an arbitrary constant. Right, notice that as expected, for a first order differential equation, we end up with one arbitrary constant. Okay, so in this case, this is the solution to this differential equation. Notice that it may be difficult or impossible to find a formula for this integral. Right, so for example, neither the antiderivative of e to the minus x squared dx, nor the antiderivative of sine of x over x dx can be computed. Depends what you mean by computed, of course, but they cannot be computed in terms of a finite number of elementary functions. Right? So if you're only allowed to use polynomials and rational functions, exponentials, trigonometric functions, logarithms, then there's no way you can find a function whose derivative is e to the minus x squared. Right? So you can solve the differential equation in that you can say the answer is an antiderivative e to the minus x squared, but you can't necessarily find an explicit formula for that solution, or a more explicit formula for that solution. Okay, the next simplest ODEs are the separable. So a differential equation that can be written in the form dy by dt is equal to f of y times g of t is called a separable equation. It's called separable because you can separate out the y's and the t's. So it's the next simplest. It's almost as easy to solve as the previous one. Right? All we do is, if f is not the 0 function, then we can solve this equation by writing, let's just put the f of y on the left-hand side, and then integrate both sides with respect to t. Right? So if I integrate on the left, I have 1 over f of y, and the derivative of y with respect to t, dt. Right? And so now this is going to be equal to the integral of the right-hand side with respect to t. But before we write that down, let's stare at this. Okay, so notice that here we have the derivative of y with respect to t times dt. And if you think back to the change of variable formula that you learned in calculus, you know that that's the same as the integral of 1 over f of y with respect to y. Right? And then, as promised, that's equal to the integral of the right-hand side with respect to t. Right? And then just for emphasis, I'm going to go ahead and put the plus c, although, as we just discussed, this antiderivative notation just means some function whose derivative is g of t. So the plus c is, if you like, already implicit there. Okay, so this is, in a sense, the solution. All that's left is to try to make it more explicit. So there's a few things to say about that. Separable differential equations are simple in the sense that the problem of solving them comes down to the problem of carrying out some integrals. But these integrals might still be hard or impossible to carry out. Explicitly. Also notice that after solving these integrals, what we would end up with is, well, over here we have a function of y, and it's equal to a function of t, right? But that's not the same as having y equals some specific function of t. Instead, what we've ended up with is a one-parameter family of curves. Some function, let's call it phi of yt equals some constant, right? These we'll call the solution curves. But you should know that they're also known as integral curves. Right? That's because old-fashioned language for solving a differential equation is that you were integrating a differential equation, because in some cases you really are just carrying out an integral. And these solution curves define y implicitly as a function of t. Right? Then it may or may not be possible to actually solve for y as an explicit function of t. Okay, so let's work out an example. Suppose we want to solve the equation dy by dt is equal to t divided by y. Okay, so here we can rewrite this, multiply both sides by y. We end up with this, integrate both sides with respect to t. Right, now here we recognize this left-hand side, right, as being just a change of variable in the integral. So this is just the integral of y dy, whereas the right-hand side is the integral of t dt. We carry out those integrals. We end up with y squared over 2 is equal to t squared over 2 plus c. So when we have this equality of integrals, right, you could have said the left-hand side is y squared over 2 plus a constant, the right-hand side is t squared over 2 plus a constant, but it's enough to just write one of those constants down. And so we'll usually do that in this way. So in this case, our solution curves are the hyperbolas y squared minus t squared is equal to 2 times c, which gives us y implicitly as a function of t. Right? We can basically solve for y, although there is some ambiguity in the sign, right? So we'd end up with y of t is plus or minus the square root of t squared plus 2c. And so, for example, let's suppose we were given an initial condition. say we were told that y of 2 is equal to 1, then, okay, plugging this in, this is telling us that y of 2 is 1, but we know that y of t is equal to this, so that would be plus or minus square root of 2 squared plus 2 times c. All right, so this tells us to take the positive square root, and that our arbitrary constant, so it's 2c, should be equal to minus 3. So therefore, the solution to the differential equation dy dt equals t over y, together with the initial condition y of 2 equals 1, is y of t equals square root of t squared minus 3, right? Which we notice is defined for t greater than square root of 3. Okay. Now, it is standard to rewrite this differential equation, right? This differential equation that we got when we divided both sides by f of y. It's standard to rewrite this, well, pretend that this is a quotient, right? It's not actually, but pretend it is. And rewrite this as 1 over f of y dy equals g of t dt. Right? So this is an equality of differential forms, right? A differential form is something that you integrate. So here, this is, of course, exactly what we got in the general case. After we did our change of variable, then we ended up with the integral of 1 over f of y dy equals the integral of g of t dt. So it's standard to just rewrite this as an equation of differential forms in this form. And then you would solve this by just integrating both sides. Now you're automatically integrating the left-hand side with respect to y and the right-hand side with respect to t. So that's what we will do moving forward. Let's go over some more examples. In particular, we can now solve those differential equations we were using last class. Now we can solve them. Those were separable equations. Okay, so first, suppose you have dy dt is equal to k times y. Okay, so of course this is separable, and what I want to do is divide both sides by y, but of course before you divide by y, you have to be careful because what if y is equal to 0? So what we'll do is we'll say, well, either y is equal to 0 or 1 over y dy by dt is equal to k. Okay, so now let's keep going with this second possibility. Right? I'm going to rewrite that as an equation of differential forms. So I'll have dy divided by y is equal to k times dt. And then I'll just take the integral of both sides. So I have the integral of dy over y is equal to the integral of k dt. And so that leads to, well, the left-hand side has integral natural log of absolute value of y. The right-hand side, I have kt plus an arbitrary constant, which I'm going to write as a. I can exponentiate both sides. And so we get that the absolute value of y is equal to the integral of e to the kt plus a, right, which is the same as the integral of a times the integral of kt. And then I'm just going to denote e to the a as b. A is some arbitrary constant, so e to the a is also a constant. It's not quite arbitrary, of course, because if you exponentiate something, you always get a positive number. So here b is an arbitrary positive constant, right? And here I had the absolute value of y. So if I get rid of that absolute value, then we end up with y of t equal to plus or minus b e to the kt. So b is an arbitrary positive constant, and now I have a plus minus. So altogether, I could say that plus minus b is some arbitrary constant, just not equal to 0. Okay, but let's put all of these things together, because I have the 0 solution, and then I have a positive multiple of e to the kt, or an arbitrary negative multiple of e to the kt. So we can combine these solutions, y equal to 0 and y of t equal to plus minus b e to the kt, into y of t is equal to c e to the kt, with now c arbitrary. Right? So it could be positive, it could be negative, it could be 0. And that is the general solution to this equation. Okay, another equation we ran into last time, right, when we were considering Newton's law of cooling. So the derivative of the temperature with respect to T was given by minus K T minus T naught. So here, K and T naught are constants. Okay, so we can reduce this to the previous case. Let's let S be the function capital T minus capital T naught. Okay, so just let's consider that function, right? What is its derivative with respect to time? Right? So the derivative of capital S with respect to time is, well, it's just capital T minus some constant, so the derivative doesn't notice that constant. It's the same as the derivative of capital T with respect to lowercase t. And we were told that that was equal to minus K times capital T minus capital T naught, right? Okay, but by definition, capital S is capital T minus capital T naught, so this is just equal to minus KS, right? So we're reduced to the previous case, right? We end up with the derivative of capital S with respect to t is equal to minus K times capital S. And so that's the same as this equation, with instead of y, we have capital S. So from here, we can conclude that capital S of t is equal to some constant times e to the minus k t. Okay, and then if we substitute that back in, that says that capital T of lowercase t minus t naught is equal to constant times e to the minus kt, and hence capital T is equal to t naught plus some constant e to the minus kt. Okay. Another example we looked at last time, the logistic equation, right? So there we had derivative of p with respect to t is equal to k naught times p naught minus p, right? So here k naught, capital P naught are constants. Okay, now this is a separable equation. So what I want to do is put these terms on the left-hand side, right? But of course we have to watch out because this could be 0, right? So when is it 0? Well, the cases we have to watch out for is when p is the function 0, or p is equal to the function p naught. And if those don't happen, then it's okay to divide, and we end up with 1 over p times p naught minus p times this derivative is equal to k naught, right? Or in terms of differential forms, what this says is dp times p minus p naught minus p is equal to k naught dt. Okay, so now to solve, we're just going to integrate both sides. So I end up integral dp times p naught minus p is equal to the integral of k naught dt. Right? So, okay, to do this left-hand side, you want to use partial fractions. So if you stare at that, you will find that it is equal to right, 1 over p plus 1 over p naught minus p. All of that times 1 over p naught gives you 1 over p times p naught minus p. Right? So that's going to be the same as the integral of k naught dt. Okay, so that means on the left-hand side, I ended up with 1 over p naught times natural log of absolute value of p plus natural log of absolute value of p naught minus p. Sorry, that's natural log of absolute value of p minus natural log of p naught minus p. And that's equal to k naught times t plus some constant, which I'll write as capital A. All right. So if we exponentiate both sides, we end up with the absolute value of p minus p naught minus p is equal to e to the p naught k naught t e to the a times p naught, right? And so let's introduce capital B as this constant, e to the capital A p naught. So here B is an arbitrary positive constant. If we remove the absolute value, then here we end up with p over p naught minus p equals plus or minus b e to the p naught k naught t. And then solving for p, we find that p of t is equal to p naught divided by 1 plus or minus 1 over b times e to the minus p naught k naught t, right? Or we could write that as 1 plus c times e to the minus p naught k naught t as the denominator and p naught as the numerator, where now c is an arbitrary non-zero constant. Right? So the general solution to the logistic equation is p equal to 0 or p equal to p naught divided by 1 plus c e to the minus p naught k naught t with c arbitrary. Right? So why was it that here we had c not equal to 0, whereas now we have c arbitrary? Well, what happens if you plug in c equal to 0? You plug in c equal to 0 here, then this fraction just becomes p naught, right? And remember, when we started, that was one of the possibilities that we had to consider separately. So we either have p equals p naught, or p equal to 0, or this, right? And so just allowing c to be 0 includes the case p equals p naught in this fraction, right? So that means that this is the general solution. Okay, let's do one final example. Let's consider the equation dy by dt equals y to the 1/3. And let's give ourselves the initial condition, y of 0 equals 0. Okay, so this is a separable equation. And we want to divide both sides of the equation by y to the 1/3. But we should be careful and first think about what happens if y is equal to 0, right? So from here, we know that either y is equal to 0 or 1 over y to the 1/3 times dy is equal to dt, right? And then if you integrate both sides, just considering this second equation, we get 3/2 y to the 2/3 is equal to t plus a constant, and we can rewrite that as y is equal to 2/3 of t plus a constant raised to the 3/2. Okay, so now let's incorporate our initial condition. We find that either y is the function 0 or y is this function with c equal to 0. So it's 2 times t divided by 3 raised to the 3/2. Okay, so we have an initial condition, and still we have two solutions, both of them perfectly good. So notice that this is problematic. Not mathematically, both of these are perfectly good solutions to this equation, but we expect that if we use a differential equation to model a physical situation, a physical system, such as a trajectory, then there should be a unique solution once we've specified the initial condition. This example shows that that's not automatic. So later, we will state a fundamental existence and uniqueness theorem which will show that for nice, whatever that means, for nice differential equations, this does not happen. Right? So for nice differential equations, if you have a first order equation and you give one initial condition, then you have one solution, right? Not like this one where you end up with two. Okay, we'll stop there and pick it up from there next time.